Hello and welcome to the tutorial on the project called as weather prediction using decision trees. So the objective of this project is to create a model, machine learning model, that can determine the type of precipitation, that means the weather conditions such as rain, snow, etc., based on the weather related input variables, right? So we can achieve this objective by using this machine learning and especially the decision tree classifier, right? So our main objective is to develop a model called as decision tree classifier, right? Then that classifier should accurately predict the type of precipitation. That means, this precipitation is the output or the dependent variable in the dataset. So this precipitation type could include the categories like rain, snow, sleet, etc. So the accuracy of the model is crucial here because that will determine the usefulness of the model. And then these predictions will made by the model are based on the input variables that are related to the weather conditions. So these variables, which are also known as features, include the data such as temperature, humidity, wind speed, wind direction, and atmospheric pressure, etc. So this model, which will develop decision tree model, that will learn from the historical data how these input variables are associated with the different types of precipitation, right? So the input variables are this temperature, humidity, wind speed, etc., and the output variable is the type of precipitation, right? So uh, that means given the input data which is related to the weather condition, our model will predict what will be the type of precipitation, right? So that's the objective of this weather prediction project. So to predict the precipitation means whether it is rain, snow, or sleet, right? So etc. So to predict that, given the weather conditions are temperature, humidity, wind speed, wind direction, etc. Okay, so that's the introduction to this project. And the dataset which we'll be using for this project is the dataset downloaded from Kaggle, right? So the dataset name is, if you go to Kaggle, there is a dataset called as weather in ZEG 2006 to 2016. This dataset you can type in Google. You will be directly taken to you will directly get a link to that Kaggle page. And then you can download this dataset from here, right? But it's around 2 MB dataset. So after you download the dataset, you will get a zip file. You can just unzip it. You will get a CSV file, right? So that CSV file we are going to use. So this is the name of the dataset, right? And then the steps which will be performing here are, the first step is the data collection and preparation, right? That so the data collection will be using the data set from Kaggle, which I just now showed you. And then we'll do something called as exploratory data analysis. The second step is exploratory data analysis. So that in that step we'll be gaining some insights into the data set, right? So we'll be checking the missing values, right? We'll understand the distribution of the important variables like temperature and humidity, and in general we'll get the feel of the data, right? And then the third step will be data pre-processing, which involves handling the missing values by filling them with appropriate statistics like the mode for the categorical variable, right? Then uh, the categorical variables which are there, especially precipitation type, will be encoded into numeric form using the label encoding, right? So this is third step, right? Data pre-processing. Then the fourth step will be, feature selection, right? So we'll select the relevant features which will be used as input for the model, right? So here the features like temperature, humidity, wind speed, then a few other things will be used, uh, and then the target variable, that is the output variable, will be precipitation type, right? So which the model will predict, right? Then the fifth step will be splitting the data set into training and testing, right? And then the sixth step will be model training. We'll develop the model, decision tree classifier model, and we'll train the model with the training data set. And then the seventh step will be model evaluation, right? So in model evaluation, we'll check the performance of the model, right, by using the evaluation metrics such as precision, recall, F1 score, etc. We'll also use confusion metrics, right? So these are the steps, 7 steps for our project, right? So let's get started with the project. So the first thing is I'll require some libraries here, libraries like pandas, numpy, and other few other libraries which will require. So let's download, let's import those library. Import pandas. So let's wait for this. So pandas is imported, right? So pandas is used for the data manipulation tasks like reading the data, data cleaning and pre-processing, right? Then we'll import the second library called as Seaborn. Import Seaborn as SNS. So the Seaborn library is used for visualization, which is based on matplotlib, and this library can be used for drawing the informative graphics or graphs, right? Then we'll need matplotlib. Import matplotlib dot pyplot as plt. So we are importing the matplotlib .pyplot module, right? So that that module is again used for creating the visualizations in Python, right? So it has functions for making plots, adding labels to those plots and setting the different styles of those plots, right? So okay, so then we'll need one more library called as train test split for dividing the data into training and testing data set. So from sklearn dot model selection model selection import, from sklearn dot model selection import train test split, right? So we are importing this train test split function from the sklearn dot model selection module, right? So this function, train test split function, is used to split the data set into two subsets, right? So one is used for training the machine learning model, and the other one is used for testing the performance of that machine learning model, right? Then I'll need one more library called as label encoder. This label encoder is the class which will help us convert the categorical data into the numerical form, because the model understands the numerical data, right? So we'll need that label encoder from sklearn dot pre-processing import label encoder, right? So okay, so we have imported the label encoder. Then we will finally not finally, but we'll need one more class for creating the decision tree classifier, right? So we'll import from sklearn dot tree import decision tree decision tree classifier, right? So here we are importing this decision tree classifier class from sklearn.tree, right? This sklearn.tree is a module. From that module we are importing this decision tree classifier class, right? So this is an algorithm used for creating the decision tree classifier model. This is an algorithm, in fact, used to classify the data or for classification tasks. So after the decision tree model, decision tree class, we'll need the performance evaluation metrics. So we'll need metrics like confusion metrics, etc. Right. So we'll import from sklearn dot metrics, import confusion metrics, comma, will also have the classification report. This classification report will contain the parameters like precision, recall, F1 score, etc. Right. So classification report, right? So confusion metrics will provide us a table sort of data tabular form, which will provide us this summary of the prediction results for this classification task. And then this classification report will be showing us the main classification matrices like precision, recall, F1 score, etc. Right? So we have imported the required libraries. Now let us import the data set and create the data frame from it. So let's do it. So weather underscore data is equal to pd dot read CSV. PD is pandas dot read CSV. We are using the read CSV function to read the data from the file, right? The name of the file, I have stored the file here in Google Colab. You can see here, this is weather history.csv, right? So this file can be uploaded here in content by right clicking on content. You can click on upload. Right after you click on upload, you will get the option to provide the path or to choose the file, right? So I have already uploaded this file here, right? Weather history.csv, which I got from Kaggle, right? So now I'll provide the name of that file here. So why I am storing there? Because I need not bother about the path and all that, right? I can just provide the name of the file, right? So that's why I am storing it in content folder, weather history. So this is Google Colab, by the way, right? If you are using Jupyter Notebook, you can upload the file there in the Jupyter Notebook, right? So weather data is the name of the data frame. This is the name of the data frame. In that data frame, we are reading this weather history.csv, right? Okay. So PD is not defined. Import pandas as PDs, I should have said. Pandas as PD, right? So PD is the short name for pandas. Okay, so now, yes, we have read the file. We have created the data frame. So now let's see the top 5 rows of the data frame, right? So we'll display the top 5 rows of the data frame. So print first 5 rows of the data set, right? So I'll print those first 5 rows. How will I print those? Print weather underscore data is the name of our data frame. So weather underscore data dot head will give me top 5 rows, right? So I'll execute this code. So we'll see, you see these are the top 5 rows, right, of our right, so of our data set, right? So these You can see here in the data set we are getting the top 5 rows, right? So these rows contains the weather history, right? So each column here represents a attribute of the weather data, right? And each row, this row corresponds to the data at different time, right? Maybe different days or different time during the day, right? So, if you see the different columns here, the first column is called as formatted data here, right? So this formatted data, so this is the date and time of the observations, and this is, if you can see, in the ISO format. This is the ISO format, right? So also time zone is included here, right? So this is the time zone, right? Then the next column is summary, right? Summary, you can see here, this column is summary. So this is the this summary is the description of the overall weather, at the time when it is observed, right? So this is partially cloud or mostly cloud in some cases, right? So then the next parameter is precipitation type or precip type, right? So this is the type of the precipitation, right? At the time of this observation, right? So it is rainy here. Here you can see it's rainy here, right? Rain, rain, rain. Then we have next as temperature, right? So temperature, the temperature in degrees Celsius, right? 9.747 degrees Celsius, right? Then we have apparent temperature, right? So this temperature in degrees Celsius, which is perceived by the humans, right? So this may differ from the actual temperature due to the wind, which wind chill or humidity, etc. Right? So this is what apparent temperature is. Then we have humidity here. This humidity means humidity in the weather, right, which varies between 0 and 1, right? Then we have here wind speed, right? So the speed of the wind. Then we have wind bearing here, right? So this wind bearing means it is the direction of the wind, the direction the wind is coming from in degrees, right? So this is the direction from the wind is coming, right, in the degrees. So here north is assumed as 0 degree, right? And then we go clockwise, right? So north is 0 degree, and then we go clockwise. Then we have visibility, right? So this means how far one can see in kilometers, right? So which this can be affected by fog, rain, or pollution also. Then we have loud cover, right? So the meaning of loud cover is uh, you know uh, loud cover, it's not the standard actually meteorological term. So it may be intended for cloud cover, maybe, right? So which indicate the fraction of the sky which is obscured by the clouds, right? So then there is pressure, right? So the atmospheric pressure in millibars, right? So it is in millibars. Then finally we have the daily summary, right? So this daily summary is the summary of the weather for the entire day, right? So this is what the data set looks like, right? So now let's move on and see, we'll do some exploratory data analysis of the data set, right? So we'll do EDA, right? EDA stands for exploratory data analysis. We'll get to know more about our data set, right? We'll become one with the data set in EDA, right? So first we'll check for the missing values. Missing values is equal to weather data dot is null. Missing values we can found by is null, and this sum will provide the sum of the missing values, you know column wise, right? So this sum adds up the number of in fact, this weather underscore data dot is null will create a Boolean data frame where the true will indicate the presence of the missing value. The missing value may be nan in numeric arrays or none in object arrays, right? So this will create the data frame where true will indicate, right? So this in fact creates a data frame, right, where true indicates that value is missing, right? And then this sum will add the number of truths, right? How many truths are there in each column, right? So that means it will tell us how many missing values are there in a column, right? So the sum will provides the number of missing values per column, right? Okay, if we do this, we'll get, if I execute this, okay, we'll get the missing values in the missing values variable, right? So this missing value is the variable which is storing the result written by this, right? So if we print these missing values now, print /n, that means we'll print our new line missing values in each column, right? We'll print the missing values in each column. So print missing value, right? So we'll print the missing values in each column, right? So let me execute this. Okay, you can see here the missing values. There are, here 517 missing values in this column, right? Precip type, right? There are 517 missing values in this column, right? Okay, so we have to handle these missing values, right? So then we'll compute the summary, right? Summary of the summary statistics for the numerical columns, right? So let us do that. Let us compute the summary for the summary statistics. Summary statistics, that is the description of the data frame or data set, weather underscore data dot describe, right? So, or you can directly write rather than storing it, you can directly write the weather underscore, right? So this is the description, we can see here, right? Description of the data set, right? So this description, these statistics include the count, mean, standard deviation, minimum 25th percentile, median, which is 50th percentile, that is 75th percentile, and the maximum, right? Okay, so now you can see here the count is the number of the number of non-missing values in each column, right? So in each column, right, the number of non-missing values, that is null values, right? So this is number of non-null values in the temperature column, number of non-null values in the apparent temperature column, number of non-null values in the humidity column, the number of non-null values in wind speed column, so on and so forth, right? So we have the non-null values here, right? Then we have mean here, right? So this is the average value, right? This is the average value. So for example, the average temperature, right, is approximately 11.93 degrees Celsius, right? So this is average for that particular column. Then we have the standard deviation of the column, right? So standard deviation, this is the standard deviation for this column, right? Then we have minimum of this particular column. So minimum temperature is minus 21.8. Then we have the 25th percentile, or it's also called as first quartile, right? So first quartile or 25th percentile, right? So the value below which 25% of the data falls, right? So this is the value below is the 25% of the data in this particular column false, right? So for example, here, this is 4.68, right? So 25% of the data in this particular column falls below 4.68 degrees Celsius, or you can say, see here in the humidity column, right? So this is 0.60, right? That means 25% of the data in this column falls below zero point 0.6, right? Then we have 50 percentile, or 50, it's also called as median, right? So this indicates the median value in the data set, right? So for example, the median temperature is 12 degrees centigrade, right? Also, if you see, the median wind speed is 9.965, right? So that is what 50th percentile is, or median is. Then the 75th percentile is also called as third quartile, right? So third quartile. So that means this indicates the value below which the 75% of the data in this particular column falls, right? For example, you see 18.8 degree is the 75th, 73rd quartile for this. Or you can see here, if we see other values like pressure here, the pressure is 1021.09. So the meaning is, the 75% of the data in this column falls below 1021.09, right? So that's the meaning of this. Then we have max. So max indicates or finds the maximum value in this particular column. So which is, in this particular column, the maximum temperature is 39 degrees centigrade, 39.9, and maximum apparent temperature is 39.3, so on and so forth. So this is what this describe gives us, right? So this describe function called on this data set will give all of the statistics about our data set, right? Okay, so all good so far. So let's move on. And now we'll do some visualization of the data set, right? So we'll do the visualization of the temperature and humidity, right? So we'll do the visualization of temperature and humidity, right? So let me plot. So visualization here we'll do. Visualization, right? So we'll plot, we'll have plt dot figure. So plt dot figure will take the figure size. So plt dot figure fig size is equal to 15,5, let's say, right? So plt dot figure is plt dot figure fig size is equal to 15,5. So what this does, so this creates a new figure for plotting, right? So this plt dot figure creates the new figure for plotting, and this fig size parameter specifies the width and the height, right? So it specifies the width and the height of the figure in inches, right? So this is in inches, right? For example, 15 inches width and 5 inches is the height, right? Okay, then we'll have plt dot subplot 1 comma 2 comma 1, right? So let us execute this. So what this will do, so this will create, this will create this kind of grid, right? So this kind of grid for subplots, right? So the parameter 1 comma 2 comma 1 indicates that there will be one row, right? One row and two columns, one row and two columns. And this one indicates, right? So this one indicates this is the first plot, right? The meaning of this is the following plot will be the first subplot, right? The following plot will be the first subplot in 1/2 grid, right? Okay, so that's what we'll have by plt dot subplot. Then we'll have sns dot histplot function from the Seaborn library, which will create the histogram, right? So the data for the histogram will be weather, will be giving temperature, right? uh, which will select the which is the temperature column from the data frame, right? So we'll have the SNS dot hist plot weather underscore data. So from weather we'll select temperature column, temperature, right? So temperature in degrees centigrade, right? So temperature, and then we'll specify the bins. Bins is equal to 30, right? And KDE is equal to true. It's a so the bins 30 means this histogram should have 30 bins, right? And then KD is equal to true means, it is this KD stands for kernel density estimate plot, right? So this KD will plot, this KD will plot the KD plot over this histogram, right? So this KD is nothing but the smooth line, right? Smooth line plot which is plotted on this histogram, right? Okay, so we'll yeah. Then we'll give the title to this, plt dot title temperature distribution, right? So this is the title for the current subplot, right? Then we'll have the second subplot, right? Second subplot for the humidity, right? So this is the we got the first subplot for the temperature. We'll have the second subplot for plt dot subplot for temperature 1 comma 2 comma 2, right? So that means the following subplot is the second subplot in the grid 1 comma 2 comma 2, right? Then we'll add the hist SNS dot hist plot weather data. Now here we'll have humidity, right? Humidity from the weather data frame, right? So again we'll have 30 beans and it's a KD plot again. Okay, so this is another histogram, and let's set the title for this, plt dot title is humidity distribution. So this is humidity distribution, right? So then we'll do the adjustment, auto adjustment of the subplot parameters, right? So for that, I'll say plt dot tight underscore layout. This is just for doing the auto adjustment, right? So then finally we'll say plt dot show, right? So plt dot show will display the plots, right? So plt dot show just displays all the figures, right? So it's kind of used for rendering the plots and to make sure they are displayed properly. So let's execute this. Okay, we have got only one plot here, humidity, right? So let me put all the code together, just just to avoid this confusion. This all code should be put together. This is plt dot figure, fig size is 15 comma 15. Then I'll have plt dot subplot, first subplot, right? Okay. Okay, so let me execute now. Yeah, we have got two subplots here, right? You can see this temperature distribution and this humidity distribution, right? So this left subplot, which you can see here, this is the histogram showing the distribution of the temperature value, right? You can see the x-axis here. This represents the temperature in degrees Celsius, and the temperature is ranging from, you can see, minus 20 degrees Celsius to 40 degrees Celsius, right? And the y-axis represent the count of the frequency count, in fact it is, or the observations for each temperature interval, right? So 2000 for this, 4000 for this, 6000 for this, so on and so forth. So this you can have here two peaks, you can see here, right? So and then we have this KD plot, right? So this KD plot, which is a smooth curve, right? So this is the KD plot, right? So this line which you can see, right? So this is in fact the probability density function of the temperature value variable, right? Then we have the humidity distribution, right? For the humidity distribution, you can see the x-axis is representing the humidity, right? As a proportion which is ranging from 0 to 1, right? 0 to 1 humidity is ranging from 0 to 1, right? And then the y-axis, again it's count, right? The count of the observations, right? And you see the distribution is skewed towards the higher frequency, right? Sorry, toward the higher humidity values. It's skewed, right? Because we have many observations near to 1, right? Which indicates that the frequency of times when the humidity is 100%, right? So the humidity is 100% here, right? So this peak here suggests that the high humidity is quite common in the data set, right? Again, this line is the KD line, which is following the shape of the histogram, right? So this KD plot just it's just smooth line, following this histogram shape, right? So again, it's peaking here at the higher humidity, right? Okay, so these are the distribution plots for temperature and humidity, right? So okay, so let's move on, and now let's write the code for handling the missing values, right? In our data set, we have only one missing value, that is precipitation. You can see here, right? Right, precipitation type, right? So that's the missing value. We will handle that missing value, right? So for handling missing value, I'll will use the mode, right? So precip type underscore will create the mode of that, right? So mode will find the mode of that column, right? Weather underscore data precip type, right? So precip type, so we'll find the mode of that. So dot mode and 0, right? So I'll tell what this 0 indicates. So then after that, I will assign this mode to the missing values. So weather underscore data of precip type, right? Which is dot fill NA, right? That means filling the null values. Fill NA precip underscore type underscore mode, right? So we'll be filling the nils with mode, right? And the in place is equal to true. Means we'll be storing those changes permanently in the data set, right? So this 0 here indicates, right? So this 0, right, of this mode, you understand, right? So this will calculate the mode, that is, mode means the most frequently occurring value, right? Mode means the most frequently occurring value in that particular column, right? So this 0 is used to select the first mode, right? If there are multiple modes, right? So there can be multiple modes. No, for example, particular 2 3 values may occur at the same number of times, so that time we'll be choosing the first, right? So this will return as the first value amongst the multiple modes, right? So okay, so and then this fill NA fills the missing values in the precip type column, right? So precip type column, null values will be filled. So let's execute this. Okay, right. So now I think if we rewrite, if we display the updated missing values information, right? So let me print this missing values after missing values after the pre-processing or handling, whether underscore data dot is null dot sum, right? So we are storing missing values in this variable missing values after, right? And then we'll print those, print missing values after handling, right? And now we'll print those, print missing after. Okay, you can see there are no missing values in this column, right? So all the missing values are now removed, right? So then I'll just use the another name for the data frame, or I can create the another copy of the data set, right? So whether underscore data underscore clean, right? Because now the data is clean, so that's why whether underscore data, right? So this is just another name of the same data set, right? This is just another name of the same data set, right? This we are just creating another reference, right? This is not the another copy, right? If you want to create another copy, we have to say whether underscore data dot copy, right? So like this copy, right? Like this you have to do. But we are not creating the another copy. This is just another name of the same data set because now the data set is clean. That's why we created this, right? Now we'll do the encoding of the categorical variables, right, by using label encoder. So label encoder is equal to, this label encoder is the name of the variable, right? So label encoder, right? And then we'll use this whether underscore data underscore clean, right, of precip type is equal to label underscore encoder dot fit transform whether underscore data underscore clean of precip type. Okay, so what we are doing here, right? So we are this label encoder is the pre-processing class from the sklearn dot pre-processing module, and that is used to encode the labels with the values between 0 and the number of classes -1, in fact, right? If there are 5 classes, so it will encode between 0 to 4, right? So this, and here we are creating the instance of this label encoder class, right? So we are creating the instance or the object of this label encoder class, and the name of the instance or object is label underscore encoder, which is a variable, right? Then we have this whether underscore data underscore clean. So what we are doing here, we are using this method called as fit transform, right? So this fit transform method fits the label encoder to the data, right? To this data, right? So this to this data by finding the unique class labels, right? And then transforming the labels into the numerical labels. That's what this fit transform does, right? So you can see, this method is applied to this precip column, right? Precip column here. Okay, so this column, this precip column in fact contains the categorical data, like strings, the strings indicating whether it's rainy, sunny, not sunny, but rain or snow, etc. Right? So these are categorical data, right? So this column contains categorical data that will be converted into numerical, right? That means categorical classes are converted into numerical, right? If there are three categories of classes, the numeric classes will be 0, 1, 2, right? So that kind of transformation is done here by this fit transform, right? So this fit transform converts the string labels or string classes into numeric form, right? And by assigning each unique string, a unique integer value is assigned, right? For each unique string, a unique integer value is assigned, right? Okay, so let me execute this. Okay, so we have done this, right? Now let's move on and select the features and the target variable, right? So features is equal to weather underscore data underscore clean. So features will be, let's say, temperature, right? Temperature, temperature, right? Then we have humidity, right? Then we have wind speed, which is in kilometer per hour, right? So we have seen above, these features. So we are selecting those features: wind speed, right? Then we have wind bearing, right? So wind bearing, right, which is in degrees, right? Wind bearing. So this is comma here, comma missing, right? So then finally we have pressure in it's like I guess in millibars, right? So okay, so yeah, after selecting these features, these are the input variables. In fact, these are the input variables which are called as features, right? So these are the weather conditions, right? These are the columns, all right? So I know we have seen here, if you see, so these are the columns, right? Temperature, apparent temperature, humidity, wind speed, wind bearing, right? Cloud cover, etc. Out of these, we have chosen only temperature, humidity, wind speed, wind bearing, and pressure in millibars. So these 5 features we are selecting to train our model to give input to the model, right? So these only 5 features we are selecting, right, from the weather data clean, right? So temperature, humidity, wind speed, right, wind bearing, and pressure, right? Okay, so let me run this. Oh, temperature, Let me copy those as it is. Temperature, right? So temperature, wind speed. I should get wind speed. Yeah, wind speed. Then wind bearing. I think only space between, right? Then okay, let me run now. Okay, yes. Then we are setting the target variable, that is the output variable or the class variable. So target is equal to weather underscore data underscore clean of. So the class variable or target variable is precip type, right? Precip type. Okay. Yeah, we have selected the features and the target variable, right? And then we'll split our data into training and testing dataset, right? So we'll split our data into training and testing dataset. So X train, comma X test, comma X train means the X will be the input features. X will be the input features, right? And Y will be the target variable, right? So or the class Y train, comma Y test, right? So X in X we'll be storing the input features, that is these, right? X will contain these, and Y will contains this precip type, right? So and X train X column will be further divided into train and test, right? So X that is equal to train test split, train underscore test underscore split, right? So to this we'll pass features. Features means why features? Because the features are these columns, features, 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 right? And the target for Y will be passing target, right? So Y is target, and the further we'll say test size is equal to 0.2, and further we'll set random state is equal to test size is 0.2 means 20% of the X will be used for training, so testing, and 80% for training. Similarly, 20% will be 20% of Y will be used for testing and 80% for training, right? So then we'll set random state is equal to 42, right? So let me run this. Yeah, we got the training and testing data set, right? So this random state 42, it's called as seed for the random number generator, which splits the data into training and testing sets, right? So using this same seed, will ensure that the split can be reproduced. That means, if we run this code multiple times, we'll always produce the same split, right? So which is helpful for debugging, for many other purposes. That's useful. That's why we use this random state is equal to 42, right? So after the splitting, we will create the decision tree classifier and train it, right? So decision tree, decision underscore tree is equal to decision, it's like decision tree classifier, and to this decision tree classifier will pass random state again, random state is equal to 42, right? And now to this decision tree classifier, we'll train this decision tree classifier with the X train and Y train. Tree dot fit X underscore train comma Y underscore train. Right. So what we are doing here, we are, from this class. So this is the class, right? So from this class, we are implementing the decision tree algorithm, right? So this decision tree, this is a variable, which is the object of this decision tree classifier class, right? So, and this again random state 42 is used to control the randomness, right? So again, for reproduction purpose, we are using this, right? Okay, so after this, let me run this code. Yeah, we have created the decision tree classifier, right? Then we have created and train our decision tree classifier with X train and Y train. Now we will evaluate the performance. Y pred is nothing but this is nothing but the variable, right? Storing the prediction result. Decision tree. On this decision tree classifier, we are calling this predict function, and to this now we are passing X test, right? So we are checking what predictions this decision tree classifier makes for the X test, right? And then after that, we'll run this, and then we'll create the classification report. So classification underscore report result, will say result is equal to, let's say, classification report, and to that report will pass the Y test, right? So Y test, actual Y's for this X's for X test, actual Y's for this X test, and the predicted Y's we are passing, right? So predicted. So this this function classification report will calculate the precision recall F1 score for this Y-pred. Right. Okay, so let me run this classification report result. We have this result now. Classification report is stored in this variable. This is a variable, right? And then also we'll store the confusion matrix. Confusion matrix result is equal to confusion matrix. Again for Y test are the actual Y's, and Y predicted are the Y-pred are the predicted Y's by the model, right? So this will compute the confusion matrix, right? So yes, we have got the confusion matrix and classification report. So now we'll print that classification report and confusion matrix. So print. So here is the classification report. Print classification report. So print classification report result, right? And then we'll also print the confusion matrix. Right, so print confusion matrix result, right? So which is the variable holding the confusion matrix. Okay, let's display this. Yeah, we have got the result of the this is the classification report. You can see precision recall F1 score and support, right? And this is the confusion matrix which you can see here, right? So the what is precision? The precision is the ratio of the true positives to the true positive predictions to the total predicted positives, right? So this precision of 1 for both classes 0 and 1, right? For class 0 precision is 1, for class 1 precision is 1, right? That indicates that every instance predicted is the correct, right? That means that is the meaning of this precision. Every prediction is correct, right? Then recall. Recall is again the ratio of true positives prediction to the actual positives, right? So this is the ratio of true positive to the predicted positives, right? Ratio of true positive to the predicted positive. This is the ratio of true positive to the actual positives, right? To the actual positives, right? That is recall. So recall one means again every actual instance of the class was correctly predicted, right? Was correctly identified. So what is the meaning of this one? The meaning of this is every instance predicted. Every instance predicted was the correct. Every instance predicted was the correct, and here the meaning is every actual instance is predicted correctly. Every actual instance is predicted correctly by the model, right? Then we have F1 score, right? It's the harmonic mean of precision and recall actually, right? So this F1 score of 1 again suggests there is a perfect balance between precision and recall, right? So in other words, it's the perfect performance of the classifier or the model, right? Then the support, meaning the number of actual occurrences of the class in the test data set, right? So this class 0 has 17101 instances, right? So class 0 has 17101 instances, and the class 1 has 2190 instances, right? So that's the meaning of support, right? And then we have the accuracy, right? Accuracy means the total number of predictions, how many total number of predictions were correct, right? So, and then we have few other things like micro average and weighted average, so on and so forth. And finally, we have the confusion matrix, right? So here you see this is called as true negative, right? This is true negative, and this is called as true positive, right? So the true negative means 17101 instances were correctly predicted as class 0, right? And here this 2190 means 2190 instances were correctly predicted as class 1, right? So this 17101 instances were correctly predicted as class 0, and this 2190 instances are correctly predicted as class 1, right? So this off diagonal elements, right, 0 0, these indicates false positive and false negative, right? And both contain 0. That means there were no incorrect predictions, right? Okay, so that's the project weather prediction using this decision tree classifier. I hope you understood and enjoyed. Thank you so much for watching. Thank you.